believe all of us involved in the satellite and telecommunications industry need to expand our vision to a broadening marketplace. During today's presentation, you will see and hear about the Gillaspie organization, what we do, and how we do it. We will provide you with valuable information on installations and servicing, and we're proud that George Takei, who stars as Mr. Sulu in the newly released Star Trek film, The Wrath of Khan, has joined the Gillaspie team in hosting this production. So roll your tape recorders, sit back, and enjoy our presentation.
From smoke signals to satellites. From the beginning of time, man has continually sought ways to extend himself to others, issuing and seeking information. For centuries, man was limited to face-to-face contact or by graphics carved upon stone. This need to communicate has brought us to the development of the most incredible systems involving the highest technologies of electronics, propulsion, metallurgy, and space. Satellites placed high above the Earth in various orbits at different altitudes, serving a wide range of communications needs. There are about 1,200 of these man-made radio and repeater stations orbiting the Earth. In this segment, we will investigate the satellite communications industry, and particularly the receiving of space signals that has allowed man to bring the world into his living room, independent of wires and distance from a transmitter. In the presentation you are about to see, we will explain the process and difficulties of amplifying a 5 to 7 watt signal that has traveled some 22,000 miles, a signal that will require amplification 10,000 times in order to be viewed on a television screen. You will meet some of the people who perform this magic, this miracle of modern high technology. We would like to gain an appreciation for development of the milestones that has brought us to space communications. We will present some tips and techniques in installing and troubleshooting systems by demonstrating 2 new devices that will assist you in placing a system in service. The evolution of communications has been, until recently, a very leisurely process. The time span can only be loosely estimated. The first state of the art in communications probably consisted of facial grimaces and hand gestures, accompanied by guttural grunts. Eventually, a spoken language evolved, and somewhat later, a form of written communication. Thousands of years pass before the development of what many scholars regard as the single greatest breakthrough in communications history, the invention of the movable type printing press. But even with the printed word, there was a need for runners and couriers on horseback. Not until the invention of the telegraph, with its staccato clatter, was any kind of instantaneous long-distance communications possible. The telephone added another dimension, but we were still tied by costly wires and cables strung over long distances. Although a pattern of rhythmic drum beats in the Congo or the smoke signal by Native American tribes may have been the first form of wireless communications, both distance and vocabulary were limited. With Marconi's invention of the wireless telegraph, communications technology accelerated and shows no sign of slowing down. Radio had been with us for some years before the exciting addition of a live picture transmitted invisibly through the air. The miracle of television was suddenly upon us. Television signals, however, are limited. They travel in a straight line, leaving the curve of the Earth and into the great void of space. And so with even the tallest transmission and receiver aerials that was practical to build, television reception was limited to perhaps no more than 100 miles. Industry was quick to rally around and compensate for this shortcoming on the part of television signals. A network of relay or repeater stations was established on high points throughout the nation. This made coast-to-coast picture and sound transmissions a way of life. But this terrestrial technology was not entirely satisfactory. Repeater stations, usually remotely located, are expensive, difficult to maintain, and are subject to the erosion and unpredictability of weather. In 1957, the first man-made satellite was launched into orbit. By contemporary standards, it was a crude device, but it provided invaluable information for the research and development of far more sophisticated hardware. Satellites can now be controlled from Earth and made to perform many tasks to serve man. They can be programmed to orbit the Earth in selective patterns and distances, or they can be made to remain stationary relative to a given point above the Earth's surface. Their applications, besides entertainment, are numerous. They photograph and transmit weather patterns, enabling meteorologists to make long-range forecasts. They are important tools in industrial communications and are heavily relied upon by the military establishment for global surveillance. The picture you are now seeing has traveled approximately 47,000 miles up and down in about a quarter of a second. It's beamed from Lexington, Kentucky, and transmitted to SATCOM-3R in stationary orbit above the equator, then relayed back to your downlink. All this at the speed of light. Here's how it works. A transmitting station called the uplink sends signals, that is, picture and sound, to a satellite 22,300 miles above the Earth's equator. Although the satellite is actually traveling many thousands of miles per hour, its speed is relative to the speed of rotation of the Earth's surface. It therefore has the effect of being parked in a stationary position at a selected point in space. The satellite operates on batteries, recharged by solar cells. Although the signal sent to the satellite is extremely strong, the returning signal to the receiving station, or downlink, is weak. Considerable amplification is required to deliver a quality picture and sound to the receiving set. Also, the returning signal strength varies according to the location. The area yielding the strongest possible incoming signal is called the footprint. The farther away from the center of the footprint, the weaker the signal to the downlink. The function of the downlink antenna is to receive the incoming signal and focus it onto a central point. The signal is then amplified to a usable strength, then sent by cable to the satellite receiver, and thence onto the television screen. The saucer-like design of the downlink antenna is similar in design and function to a solar reflector, wherein the light and heat of the sun is gathered and concentrated onto a single point. In the case of the satellite antenna, the focal point is also the first stage of amplification. Next is the low noise amplifier, or LNA, which provides the first stage of electronic amplification. Then a down converter changes the signal to a more usable frequency. The receiver fulfills a variety of functions. By supplying power to the LNA and down converter, it further amplifies and modulates the signal, as well as providing channel tuning. The capturing of the satellite signal and delivery of it to the television set must be carefully done. Any intrusion of noise, any faulty circuitry will interfere with the signal quality. From concept to development, the receiving device must be expertly designed to enhance the delicate signal to its maximum.
Engineering is the process of taking present-day technology into a practical form by actually building reliable products that can be used for our own well-being. At Gillaspie Associates, we are marching towards this principle on two fronts. First, with the research and development staff to bring tomorrow's ideas to light today, and secondly, with the product development staff to launch these new ideas and technologies into a reality. Developing a reliable satellite receiving system is an exciting challenge, even by today's standards. amplifying a signal that has come 22,300 miles from a spacecraft, which by the time it gets to the Earth is less than 1/1,000,000th of a watt, requires some real special attention. First and foremost, the signal must be amplified 10,000 times and concentrated into one place. This is the primary mission of the dish antenna. Secondly, this minuscule signal must be amplified again 100,000 times, but now with a low-noise electronic amplifier. Finally, our space-emanating signal is strong enough to operate on. But prior to this, we were confronted with not actually being able to distinguish between what was signal and what was noise. But now that we have a strong signal from the LNA, extracting picture and sound information from it is relatively straightforward. But the challenges are not over. Our research and development staff is tenaciously striving for improvement. As with other technologies, ours is no exception. Additional products and accessories are emerging. And, as always, Gillaspie Associates is riding the wave of advanced developments in the satellite industry.
Those that have installed satellite systems know the true test of this technology. This is where it all comes together. The antenna, the LNA, the cable, and the receiver. This is where the real expertise is required. The installation technician must be a little bit of all of the experts that created the product. A mechanic, an electrician, an astronomer, a carpenter, an electronics technician. He's all these. Proper product selection and manufacturer support make your installation job easier.
Developing installation test equipment is another vital link in the chain of bringing satellite television into your home more economically and efficiently. It is for this reason that the Gillaspie Model 5800 satellite receiver test set was developed. By merely erecting a portable dish antenna, mounting the low-noise amplifier, connecting it to the field test set, we have erected a completely operational earth station in a matter of minutes. For testing purposes, the need for commercial AC power, a trailer-mounted antenna, satellite receiver, TV set, and the complicated system wiring is a thing of the past. Doing a site survey such as this is the first and most crucial step in erecting an earth station at any location. It is vitally important in selecting a site that is free from any interfering signals and from signal blockage by trees, buildings, or virtually any object. The Gillaspie Field Test Set is an invaluable instrument to meet these needs. But the site survey is not the end. The actual customer installation is yet to come and must be installed with utmost care. Proper mechanical and electrical integrity at this phase is crucially important as building and testing the receiver, for the entire system is like a finely knit chain which cannot have any weak links. A good concrete foundation, properly dressed cables with good mechanical as well as electrical connections, and proper equipment mounting will look good and function well under any and all environmental conditions. Time well spent here should provide trouble-free operation for many years to come and peace of mind to the installer as well as the customer.
Okay, another invaluable instrument designed by Gillaspie Associates is the remote meter, designed for doing several things in the field. One of the unique things is that once you get it connected to the IRM, you can remotely control it. You can do several things that would be impossible to do without this type of an instrument. It allows you to make signal readings, align the dish. If you're looking for a satellite, you can put the unit into the scan mode and it will automatically scan the channels or through the various transponders and allow you to find the signal. You can use the unit several different ways. The way it is set up now, it is actually being tuned from inside where the receiver is located at the television set, and we can flip a switch and we now have control over the transponder tuning with with this pot right here, which can be calibrated so that the channels are actually indicated as the transponders are. And we can tune through it, and the meter will move and showing you the relative strength of the signal. And it's also very handy for locating the satellite, which you may not be sure which transponders are on the air. So at that time you would flip the unit into the scan mode, and it will scan across the various transponders, starting at the low end, working up to the high end. And once it reaches the high end, or the highest channel, it will start scanning backwards again. It scans at 2 different speeds, which is quite unique. So the scanning feature is very straightforward. Now in the tune mode, let's say that we have definitely found a satellite now. We can flip the tune and lock onto a specific transponder, peak it here, and then we'll move out and peak the dish. And this is where the neck strap comes in. Very handy. It leaves you hands-free. You simply just watch your meter, grab your dish, and rotate it just a little bit. The meter will dip, and we'll push it back to where we want it. We'll peak the meter, and we have indeed found the strongest point for this antenna aimed at this satellite. Another useful feature with the M76 remote meter, and I'm sure you as an installer have run into this, is trying to get the LNA properly focused into the center of the dish. Now, this generally requires 2 people, one person to be down looking at the receiver's signal strength meter, and you up at the top of the dish on a ladder trying to maximize the focal length of the antenna, or the LNA. So with the remote meter, you simply strap it around your neck, climb up to the top, tune in a transponder, loosen up your LNA, which is a very difficult thing to do when standing on top of a ladder, and simply adjust the focal length. Peak the meter, and when the meter is peaked, it is set. It's that simple. There's no one down below looking at a meter, yelling at you as you go through the dip and onto the other side, or through the peak into the other side. And you've already passed the peak, and he yells, and you stop, and you think it's properly focused when it isn't. This way, you've got the meter dangling from your neck. It's a very simple thing to do, and you can check various transponders and make sure that things are working properly. Very useful. And that's that. The customer calls up and says that beautiful system that you installed for me last week or last month isn't working, and I'd like you to come out and check it. Well, this is where the field test set comes in very handy. Completely self-contained power supply, television, receiver, LNA power supply, meter, everything can be done right out at the dish. You start out simply by checking pieces one at a time. Disconnect the power from your down converter. Remove the RG8 cable that is feeding the LNA. Plug it into a jumper or directly into the test set if the cable will reach. Hook the cable up the other end of the RG8 up to the test box. And put the unit into the battery position, like so. Turn on the LNA power, because we're now powering the LNA by from the battery pack, which is located inside the tuner. Tune in a transponder,
we would get out of this reduction program
and
as soon as the economic
you have now checked and verified
we get out.
that your LNA
And we have told
is in operating condition.
the integrity of the program
After this is done, and you're sure that the LNA is functioning properly, go through a couple of transponders to verify that, while looking at the signal strength on the meter and also checking the picture quality, listening for audio. Once you've assumed, or once you've established that the LNA is functioning properly, turn the power supply back off, reconnect the LNA to the down converter, and now we'll proceed with the same test box to test the down converter, which has been permanently installed. Turning off the LNA power. remove the RG8 and put it aside. Take a jumper, which is supplied with the test set, plug it into the external IRM, remove the IF jumper cable, and insert a piece of RG59 into the receiver IF in port. Again, making sure that the unit is in the off position. Simply run these cables over to the down converter, which you are suspecting is malfunctioning. Disconnect the 70 megahertz line that feeds the receiver. And hook up the cable from the test set. Plug in your power. After you've connected the IRM that is suspected of malfunctioning, put the test set internal IRM, external IRM switch into the external IRM position. Turn the power to the test set on, wait for the TV to warm up, and simply tune the IRM with the external IRM tune knob and through the various transponders. And again, you can see that the IRM is functioning. The next step, since you've established that the IRM is working, the LNA is functioning, the dish is pointed at the satellite, we will now check the DC cables and the RF cables that run into the house. So again, turn the unit off, reconnect the down converter after checking all connections, reconnect the down converter as it previously was, and then carry the test set into the house and perform the same test inside.
We've come a long way since the smoke signal. Satellite communication, like the printing press, the telephone and telegraph, is not the end. There's still significant progress required before the perfection of the art of satellite communications can be realized. Those of us at Gillaspie have dedicated ourselves to this perfection, from the engineers in R&D to the order desk, from the shipping department to the test bench. The Gillaspie staff is never satisfied that we have arrived. New and better ways are being pursued to provide the best product for the most affordable price. We're investing heavily into the future because we plan to be there, always in the lead, setting the pace. But we need your help to provide you with the best. Gillaspie is here to serve your needs. We need to know those needs. Satellite communication is a significant advancement in technology that offers to serve man's need in his search for self-expression. Good day. I'm George Takei for Gillaspie Associates.